Hello, everybody. Welcome to Unit 2.3 Independent Study Practice Problems. Today we're doing problems about kinematics, so more kinematics, but we're also doing air resistance and parabolic motion specifically. So let's get into it. And I just want to say, today I'm going to be adding a few extra things. So we're going to be using some labs to help explain the concepts, and we're also going to be using demonstrations from different videos on YouTube to show some of these concepts in action. So let's start with the first problem. 1. A car initially traveling east with a speed of 5 meters per second is accelerated uniformly at 2 meters per second squared for 10 seconds along a straight line. During this 10-second interval, how far did the car travel? Okay, so let's just underline everything we know from this question. So let's start with the initial speed. We have the car initially traveling east with a speed of 5 meters per second. Well, then it should be pretty clear then that the initial speed, VI, velocity initial, is 5 meters per second. So initial velocity is 5 meters per second. And then is accelerated uniformly at 2 meters per second squared. And so acceleration would be 2 meters per second squared. And then 10 seconds along a straight line. So we have 10 seconds. During this 10-second interval, how far did the car travel? When we hear how far does the car travel, what do we think of? How far? Displacement. And so we do D. So then let's set up a little table over here on the left, just a little table. And let's label everything we've been given. So initial velocity, final velocity, displacement, acceleration, time. I'll zoom in on that a little bit. What was the initial velocity? Well, we have it here. The initial velocity was 5 meters per second. So we're going to put 5 meters per second, and then uniformly at 2 meters per second squared. So we can put for the acceleration 2 meters per second squared, and then 10 seconds. We've already kind of done all the hard work. We've read the problem, so now we're just plugging it into our table. And then what do we know about final velocity? Does our question here say anything about final velocity? Not really at all. There's nothing in this whole question about final velocity. And because of that, we're just going to write NA for final velocity. Just going to write NA, so we don't know what it is. And then displacement. We're also not given anything about displacement, but we're not going to write NA because we are given a little piece of information, and that is we're trying to find displacement. We have right here how far did the car travel. So I'm going to write, you can write a question mark, find, whatever floats your boat. Okay, so let's label that as G. So what we're given. It can be really helpful to label the steps we're taking when we solve the question. And so now let's go on to E. Let's find the equation we should use while solving. And so to do this, let's look at the 3 equations we can use for kinematics here. We can use these 3. The first one, I'll just label them here so we can always use them, is the final velocity equals the initial velocity plus acceleration times time. Second equation we have is the displacement equals initial velocity times time plus 1/2 acceleration times time squared. And then the third equation we have is final velocity squared equals the initial velocity squared plus 2 times acceleration times displacement. So those are the 3 equations we have. And now this is another crucial step. We need to pick which equation we want to use. And so to do this, or to pick whichever equation we want to use, not even just in physics, well, we want to see which equation has what we're trying to find. Well, what are we trying to find? Right here, we say we're trying to find displacement. We could say right here, we're trying to find displacement. And then which of these over here has displacement? Well, we know one of them doesn't have displacement. One of them says no D, and that's this one. There's no variable D in there to represent displacement, and so we can't use that equation for this problem. But then we have 2 left, and so how are we going to pick between those? Well, what do we not have? Well, we are not given final velocity. remember we were not given anything about that in the problem. And so because of that, we do not want to use the equation that has final velocity, okay? So which of these has final velocity? Number 3. So we do not want to use number 3. We do not want to use the equation that has the variable we weren't given, right? Okay. So now that we have that equation, let's mark that one down. So that's one that we're using for this. I'm going to uncross those out so we can still use them later. So we have displacement equals initial velocity times time plus 1/2 acceleration times time squared. Okay, so now it's really just plugging in the values, right? So let's plug in these values into our solve. So let's solve. Displacement equals, well, what's initial velocity? We have right here, initial velocity is 5 meters per second. So 5 meters per second times how many seconds? We have right here 10 seconds. We're just plugging in things. This is just algebra. Plus 1/2 times what's acceleration? 2 meters per second squared. Oops, sorry. 2 meters per second squared. And then what's time? Well, time is 10 seconds, like we said before. So 10 seconds. And then remember, it's squared. Do not forget this crucial step. So this squared is going on the outside right here. Great. Now let's go to the next step. We're just going to solve. So what is 5 times 10? 5 times 10 is 50. I'm just doing this part right here. 5 times 10 is 50. And so we get 50. And then what are the units going to be? Remember that for this section here that we're solving right now, we're going to get to this section later. Don't worry, we're not forgetting about it. For this section, we need to also, and for all these sections, we need to multiply units as well. So just like we did 5 times 10 is 50, we also need to do what is meters per seconds times seconds. Now, sometimes it can be a little tricky to see, and I understand for when you have it in this format, but let's try to bring it into a slightly different format to make it easier to see. So over here, I'm just going to show you meters, meters per seconds times seconds. That's what we have right over here. We have meters per second times seconds. Now, in this format, it should make it a little bit more clear that we can just cancel these out, right? So, since we can cancel those out, this becomes meters. And if you really want, if you don't believe me, then first of all, you can use a mathematical proof. But if you don't believe me, then you can just say, well, displacement is in meters. Right? When we're doing displacement in science, we're using meters or kilometers or a different unit of distance. But if we're using meters, it would make sense because we're getting displacement. If you got the answer meters per second squared here, that wouldn't make any sense because you're solving for displacement. Okay, and meters per second squared is not a unit of displacement. Okay, so you can just use logic to justify a reasoning sometimes. It's always good to do that. Great, so we have 50 meters. Then plus, let's do that other side here. Don't forget about that. Well, we have, first we have to simplify this 10 seconds squared because there's an exponent. Well, similar to how we multiply the units, we also, when we have an exponent, we need to bring that into the units as well. And so when we're looking at how we want to simplify this 10 seconds squared here, it's important that we don't just make it 10 seconds squared, but we make it 100 seconds squared. And why is that? Well, that's because we had 10 seconds and then all of it was squared. And so this squared applies to the 10 and then it also applies to the seconds, okay? That's a mistake that a lot of people make, and I understand, but I'll let you know now so that you don't make that mistake in the future. So then we have, what's 1/2 times 2 times 100? Okay, 1/2 times 2 times 100 is 100. So we have plus 100. But then what is meters per second squared times second squared? Well, similar to what we did before, meters per second squared times second squared. We can cancel these out like how we did before. So let's do that. Let's just cancel these out. Amazing. So now we cancel those out, we get 100 meters. And what is 50 meters plus 100 meters? Well, since they're in the same units, we can add. So that would be 150 meters for our displacement. Great. Now, before we move on to the next question, I just want to bring this into a lab that I found online so that we can make sure our answer was correct in a real life scenario. And just consider this lab has a walking man, but let's imagine this walking man is a car. So let's get into that.
Great, so you can see here we're in the simulator and we have this very nicely dressed walking man over here at negative 10 meters. And what we want to see is if we set the velocity to an initial velocity of 5 meters per second and an acceleration of 2 meters per second squared, like the problem says, how far is this man going to be displaced in the end? Well, what we need to do is since we calculated a 150-meter displacement, and we only have 20 meters for our range here, we need to divide all of the velocity and the acceleration by 10 so that we can work with this 20-meter range. And so in the question, we were given a 5 meter per second initial velocity, and so I'm just going to set a 0.5 meter per second initial velocity. And then for acceleration, we were given 2 meters per second squared. I'm going to set it to 0.2 meters per second squared. And then we will see after 10 seconds, how far is this man going to travel? Let's see. And before we do this, is this man going to stay at the same speed or increase his speed over time? Well, he's going to increase his speed over time because we have an acceleration, and acceleration means increasing velocity over time. Great. Let's start it in 3, 2, 1, go. Great. So there's 10 seconds. And let's see where the man is. Well, you can see that we have negative 10 meters over here and 5 meters here. And so what's the difference between negative 10 meters and 5 meters? That's 15 meters. But remember, we have to multiply by 10 to get what we had in our problem, because we divided the acceleration and the velocity by 10 because we wanted it to fit in this range. So what's 15 times 10? 150. That means we got the right answer.
Okay, great. So let's get into problem number 2. 1 kilogram mass was dropped from rest from a height 25 meters above Earth's surface. The speed of the mass is determined at 5-meter intervals and recorded in the data table. Using the information in the data table, construct a graph on the grid following the directions below. A. Mark an appropriate scale on the x-axis and label this height above Earth's surface. So let's just do that step. Let's take it one step at a time. So for that first step, let's mark an appropriate scale. I think it should be pretty clear that since we have data going from, for the x-axis going between 0 and 25 meters, and we have 5 different lines given to us right here, well, we should just split that and divide it and make each of them 5. So then we'll have 0 meters, right? Then 5 meters, 10 meters, and 15, 20, and 25. And then don't forget to mark the x-axis like it says and label it height above Earth's surface. So let's do exactly that. Height above Earth's surface. I'll just write an S for myself, but for you, you should just write the whole thing. So we did that. Great, let's check that off. And next, let's plot the points for speed versus height above Earth's surface. So we can just look at our data table and plot the points. I'll do this in blue so it's very easy to see. So when it's 25 meters above Earth's surface, what's the speed of it? 0 meters per second. And This will be a lot easier if you really think about what's happening. So think about, well, why would the speed be 0 meters per second, the velocity be 0 meters per second when it's at 25 meters? Again, I just want to bring you quickly into a little lab to show you why this is true. Because I also think that before we solve it, knowing the actual concept will be make it a lot more clear of what with what we're actually doing. Great. See you after that.
Great, so here we have the free fall simulator. And let me just show you a few things. I want to show you, well, what happens to acceleration when the ball is dropped, what happens to velocity as the ball is dropped. So let's start with the velocity before the ball is dropped. Well, why is the velocity 0 meters per second? Well, that's because since we have time as 0, the acceleration due to gravity has not had time to pull the ball down. And remember, acceleration is the increase of velocity over time. By how many meters per second is the velocity increasing by every second? And so right now, we have the velocity as 0 meters per second because there's no time. But as we click play, which increases the time, let's look at what happens to velocity. What I want you to do is, as the ball drops, look at this velocity here and see if the arrow grows bigger, smaller, or stays the same. I'll let you take a guess now. What happens to velocity as we drop the ball? Great, let's do it. You can see as we drop the ball, the velocity gets greater and greater. You can see that velocity vector right here. And that velocity vector is getting longer and longer, which means you can see now it's at 35 meters per second. And then now I want you to look at this red line. What happens to acceleration as we drop the ball? Well, acceleration will stay constant. Why will it stay constant? Because the acceleration due to gravity is always the same. It is not changing. So as this ball drops, the acceleration stays the same.
Okay, great. So now that we know what we're working with, let's plot our data points. So like we just covered, at 25 meters, which above Earth's surface where it's starting, the speed will be 0 meters per second. And then at 20 meters above Earth's surface, the speed will be 9.9 meters per second. And so we go on our x-axis to 20 meters, and then we go to 9.9 meters per second. That would be right here. Amazing. And so then we do 15 meters would be at 14 meters per second, like it says right here. We're just graphing. It's 14 meters per second. Okay, and then at 10 meters, what's the speed? 17.1 meters per second. And finally, or almost finally, at 5 meters above Earth's surface, so it's almost on the surface, we have 19.8 meter per second velocity. And then, what's the velocity like we just covered? At 0 meters above Earth's surface, the velocity is 22.1 meters per second. 22.1 meters per second. Great, so we just graphed all of them. We have, you see that trends that we will now graph, but we're going to graph it using a curve of best fit, which is what the next step tells us to do. So we did this, great. Plotted the data points. Now what I want to do is, or what the directions say, you have to draw a curve of best fit. Now, like it says, we do not want to do a straight line or connected dots. Rather, we approximate a curve. And so when we do a line of best fit, we're almost splitting the data points in half symmetrically. And so let's do that using a curve. This does not have to be perfect here. We're just doing this for practice. And so let's do our best, or I'll definitely do my best to draw a curve of best fit. Notice how not all of the data points are on the line, but they're symmetrically mirrored on both sides. And so we have this data point is here, this data point is here. You can see that some of the data point is on this side of the line, some of it's on this side of the line. It's like if we had two lines here, right? Something going through it symmetrically would be like this. So that's what we're doing for our line of best fit there, or curve of best fit, rather. Great. So we did that. We drew the curve of best fit. Now, using the graph, determine the speed of the mass after it has fallen a vertical distance of 12.5 meters. Now, this one can trick some people because remember that falling a distance of 12.5 meters doesn't mean it's 12.5 meters above Earth's surface. If I fall 12.5 meters, I will be way higher than 12.5 meters above Earth's surface, okay? And by the way, let's just imagine I'm skydiving. So we're 12.5 meters above Earth's surface. It's 25 meters above 0 meters. So that would mean we have 0 meters above Earth's surface here. So 12.5 meters above Earth's surface would be right here. You can even label that as 12.5. Great. And so let's look where on our graph would that intersect with our curve of best fit. And so let's work our way up and look at 12.5 meters above Earth's surface. Well, that looks like it's about 14.5 meters per second. So that would mean that after it has fallen a vertical distance, the mass has fallen a vertical distance of 12.5 meters. This object is now going 14.5 meters per second. And before we move on to the next question, I just want to say that everybody is going to graph this curve a little bit differently. And so if you didn't get exactly 14.5 meters per second here, it's fine. In this, everybody's graphing a little bit differently. I'm just, hopefully you didn't get 10 meters per second or 25 meters per second. If you did, then just rewatch this video, follow the steps, and then you'll be fine. Okay, great. So let's move on to question number 3. And I do want to say that this is a concept question. And so what I want to do is bring you to an amazing video by Brian Cox, where he goes into a vacuum chamber and drops a feather and a bowling ball next to each other, but then he does it inside a vacuum and then not inside a vacuum. And what we'll look at is, well, what's the difference inside a vacuum versus outside of a vacuum, and how can we use that to answer a question? Great, so let's get into that.
So here we have Brian Cox in the world's largest vacuum chamber. And I'm going to play the video, and what he does is he drops a bowling ball and a feather simultaneously inside of a vacuum and then outside of a vacuum. Now, just in case you don't know, inside of a vacuum, that means that there's no fluid, so no air. Outside of the vacuum, just like how we're living right now and how you're doing your homework right now, there is air. There's air all around us.
So the conditions of outer space.
So let's look at that drop. Remember, this is the drop with air. Okay. So let's look at the forces acting on these objects. Well, there's gravity pulling down on the bowling ball. You know that, of course. We will learn about forces in the next unit, but I'm going to simplify this because you don't really know too much about them yet. So gravity is pulling down on the bowling ball. But then is gravity also pulling down on the feather? Yes, of course gravity is pulling down on the feather. But then, what forces are in the opposite direction? Well, both objects have air resistance. There's air resistance for the bowling ball, and there's air resistance on the feather. But then why do they behave differently? Why do they accelerate differently? Well, the feather has a very low mass, but a high surface area. And because of that, there's a lot of space for air molecules to hit the object, meaning you can almost visualize there's all these air molecules around the feather as it's falling that it has to run into. And the same thing for the bowling ball. But for the feather, its low mass means that the air molecules can have a greater impact on its acceleration. You can imagine dropping something super heavy like an anvil through the air. It's not going to care too much about these air molecules because its weight will totally overrule these air molecules. With a feather, though, air molecules have a significant effect on its acceleration. And then because of that, at some point, air resistance, the force due to air resistance, will be equal to the force due to gravity. And when that happens, it will stop accelerating. And when it stops accelerating, it reaches a terminal velocity. With the bowling ball, however, there's very little effect from air resistance, and so there's still a net positive acceleration in this direction. So let's play the video and see what happens as it keeps falling, just to have a better way to visualize it. You can see here the feather stops accelerating. It does that back and forth swinging motion. At this point, the acceleration due to gravity is equal to the force due to air resistance. And so there is no acceleration. This feather keeps going at a constant velocity downwards. And remember, constant velocity means no acceleration. Great. Now, what I want you to do is predict what will happen when there is no air in this space. Well, think about this before you make a guess. What will be pulling down on the bowling ball? What will be pulling down on the feather? And then what will be trying to stop the bowling ball, and what will be trying to stop the feather? Think about that, and then we will go to that section and see what happens. Great, so let's go see that. It's very ominous what's happening. You can see the doors are closing and air is being sucked out of the chamber. Okay, this is amazing. We can see the bowling ball and the feather both falling with the same acceleration. So this bowling ball, again, has the force due to gravity pulling down on it. 9.81 meters per second squared. Gravity. And then, is there going to be air resistance pulling up? No, there are no air molecules here for the bowling ball to run into. And because of that, there is no resistance in the bowling ball. Same thing with the feather. There are no air molecules for the feather to run into. And because of that, there's no acceleration vector this way. There is, though, however, still the acceleration vector down due to gravity here. So, also at 9.81 meters per second squared. Gravity. And you can see that these vectors are both on the object, and they are going to accelerate at with the same magnitude. Great, so let's finish watching the video. Remember, they're not running into any air molecules. The feather will keep accelerating. It will not reach its terminal velocity. So, what can we say? What can we say to summarize this? Well, objects inside of a vacuum with no air accelerate at 9.81 meters per second squared, no matter what their mass is. You can see that a bowling ball has you know that a bowling ball has much more mass than a feather. But since there's no air, it does not matter. They will both accelerate at 9.81 meters per second squared. In the real world, however, which is not a vacuum,
Air resistance.
the feather is slowed down by air resistance. And so at some point it reaches a terminal velocity and stops accelerating. The bowling ball, however, also runs into air resistance. It also has air resistance. But the mass is so great of the bowling ball that it has a greater ratio of mass to surface area, and so it overcomes that air resistance. So when air resistance does matter, not inside of a vacuum, mass does matter when it comes to the acceleration of the
Of air resistance.
Okay, so now having seen that video, we should be able to answer this pretty easily. We can say that inside a vacuum, there's no air resistance on the object because there is no air, because there's no air inside of a vacuum hitting the ball or the feather. But without a vacuum, there's air and therefore air resistance hitting the feather or the object. And because of that, there is going to be a terminal velocity of the object. So it's not going to keep accelerating at 9.81 meters per second. You obviously do not have to write as much as I just said, but if you explain something about terminal velocity and you explain that the air is running into it, and so there's air resistance, that should be a great response. Okay, so let's move on to question number 4. An object is dropped and falls freely towards Earth. How much time has passed since by the time the speed of the object has reached 9.81 meters per second? And so here it's really important to look at what we're given too, but it almost looks like we're given nothing. However, what we have to do is really read the problem and find out what we're given very carefully. So let's make our table and label initial velocity, final velocity, displacement, acceleration, and time. And now let's look through our problem and see what we're given. Well, an object is dropped from rest. And what does rest mean? Well, if something's resting, that means it's not moving. And so we can say that the initial velocity is 0 meters per second. Great. And then what can we say about the final velocity? Well, by the time the speed of the object has reached 9.81 meters per second. Now, sometimes that can be a little bit unclear why that's the final velocity, but because it will keep accelerating, considering if it does not hit an object and it stops moving. But we're looking at the time frame between its rest and its how the time it reaches to take 9.81 meters per second. And so since we're looking at this time frame, the final velocity will be 9.81 meters per second. And then what is the displacement? Well, we don't know anything about displacement. It wasn't given to us, although we could find that in the future. So we can write an A for that, or you can write an X, you can write whatever you want. And then for acceleration, well, it falls freely towards Earth. Well, at low altitudes, things fall with no air at 9.81 meters per second squared. And remember that unless we're told that we're including air, we are neglecting air resistance when we're doing physics here in this class. And so let's write acceleration 9.81 meters per second squared. And then time, I think it should be pretty clear how much time has passed. And so for time, we can say question mark, fines, whatever floats your boat again. So let's go, and I'm labeling G for what we're given. Great, so now let's get into our equation. So let's go on and head back to our 3 equations, and let's look at, again, what we're given and what we don't know. Well, we're trying to find time, and we do not know d. We do not know displacement. So let's look for an equation that does not have d and does have t. Well, these both have d, so we can't use them. This one's very clear. D right there, so we can't use it. And t here, so we can't use it. So that means we have to use equation number 1. And that's great because in my opinion, it's the simplest. Let's go back and say the final velocity equals the initial velocity plus acceleration times time. But then we're trying to solve for time, and so we need to manipulate the equation so we are solving for time. Now, rather than first plugging in the values, then rearranging the values, it's so much easier to just rearrange the equation with the variables. And so let's bring the initial velocity over, and that gets us the final velocity minus the initial velocity equals acceleration times time. And then we'll divide by acceleration to get time. So time equals the final velocity minus the initial velocity over time. Sorry, over acceleration. Amazing. So we have the equation and we can plug in our values. Let's do exactly that. So time equals the final velocity minus the initial velocity divided by acceleration. And so let's plug in our final and initial velocity. So time equals, what's our final velocity? 9.81 meters per second minus, well, initial velocity is 0 meters per second, but we'll still write it down. And then what's acceleration? 9.81 meters per second squared. And so that leaves us with time equals 9.81 meters per second over 9.81 meters per second squared. Then we're doing, remember, we're dividing the units and the values too. We're doing both of them. And so what's 9.81 divided by 9.81? Well, any number divided by itself is 1. And so time equals 1. But then what's meters per second divided by seconds? To make that nice and clear, I'll do meters per second, right? Divided by meters per second squared. And so what we can do is we can cancel out the meters. We can draw this line here as a denominator to separate the numerator and denominator. And we can cancel out the meters, okay? And then we have the second and second squared. And so that means we can cancel out one of these. That gets us seconds. So time equals, so what is it? Oh, 1 second. Great. And I do have to tell you, I'm so sorry that we did not even have to use all of this math to solve this question. We could have just done this conceptually. And why is that? Well, what does meters per second squared really mean? What it means is that by how many meters per second will the speed increase every second? And so that means if it's 9.81 meters per second, it's increasing every second. That means it will take 1 second to reach 9.81 meters per second. Now, if that is a lot of meters per second and it is hard to understand, let's now go into another lab and I'll show you if this is the correct answer. And we'll do this using another simulator.
So here we are again in our free fall simulator, and on the right we have a graph of time versus velocity, and then on the left we have a little image of what is actually happening. So let's play the simulation until the time is 1 second and see, well, what happens to the soccer ball. How many meters per second will it go? Then remember, there is a 9.81 meters per second squared acceleration, so we calculated that it will take a certain amount of time. Let's see if that is the case. Ready? 3, 2, 1, go. Now, I played that for 1.25 seconds, but we can use our graph to see, well, what was the velocity at 1 second. So if we read this graph and we go to 1 second, what will the velocity be? The velocity will be, you can see on the middle of the screen on the bottom, there's something that says x1, which means that the time is 1 second, because the time is the x-axis, and y, negative 9.8, negative 9.82, around negative 9.81 meters per second. So our answer was correct, and I will explain why later.
Great, so let's now move on to question number 5. A ball is thrown straight downwards with a speed of 0.5 meters per second from a height of 4 meters. What is the speed of the ball 0.7 seconds after it is released? So, as always, we have our data table, and we have initial velocity, final velocity, displacement, acceleration, and time. But we need to read our question and plug in the values. A ball is thrown straight downward with a speed of 0.5 meters per second. Before I continue, I do want to say that we need to label. Remember, we're looking at a vertical a vertical plane of up and down because we have thrown straight downwards. We're not looking at horizontal motion. This is just vertical motion. Remember that vertical and horizontal motion in physics is independent. And so, since we're looking at vertical motion, and you do the same with horizontal motion, we need to say which way is positive and which way is negative. Well, often I like to say that the first direction we're looking at is positive, and so that's why I'm going to say downwards is positive. And when you think about it, our whole question we're solving is going downwards. And so we should label it as positive so we don't have to always use negative numbers. So that's just me talking through my reasoning of why I'm labeling that it is 0.5 meters per second instead of negative 0.5 meters per second. Remember that a negative is just the opposite direction in physics, okay, in kinematics. So we have the final velocity. What do we know about it? Well, we're trying to find the final velocity. So I'll write find. And then it says 4 meters from a height of 4 meters. But here's the thing. This height of 4 meters is really irrelevant if you think about it. If we're dropping something from a height of 4 meters, it doesn't matter how high we're dropping it from. We're just trying to find the speed after you drop something for 0.7 seconds, okay? So the height of 4 meters is irrelevant here. So what we can do is we can write, doesn't matter, you can write NA, not given anything about it. And then the time, we're given 0.7 seconds. And then acceleration, well, remember, on Earth, it's 9.81 meters per second squared. So 9.81 meters per second squared. So now we need to pick an equation. And which equation do we want to choose? Well, just like the last problem we solved, we do not know anything about displacement, okay? Or at least do not know anything that will help us solve this problem. And so, which equation does not include anything about displacement? Well, the first equation, the final velocity equals the initial velocity plus acceleration times time. So let's write that again down there and solve. We're just plugging in the values like before. So, final velocity equals the initial velocity plus acceleration times time. But then what are we solving for? We're solving for final velocity. And that means we can keep it in this format because it's already in terms of final velocity. Final velocity equals blank. That's what we want for this question. So now let's just plug in our values. This should not be too hard. Final velocity equals, what is our initial velocity? 0.5 meters per second plus 9.81 meters per second squared times 0.7 seconds. So let's do each side of this equation. We have 0.5 meters per second. And then what is 0.7 times 9.81? Well, that is 6.87. So plus 6.87. And then what are the units going to be? Well, like before, we're doing meters per second squared times seconds. And so we're going to divide. And so this seconds cancels out with this squared here. And so we get meters per second. And that should make sense since we're solving for final velocity, and velocity is in meters per second, right? So that's why we're getting meters per second. And so then what's 0.5 times 6 plus 6.87? That is 7.37 meters per second. Great, that's your answer. Let's move on to number 6. A ball is thrown vertically upward with an initial velocity of 29.4 meters per second. What is the maximum height reached by the ball? Okay, so at the end of this, we're also going to go into the simulator to check our answer. But first, let's see what we're given and create our table like always. And so what do we know? We know that it is thrown upwards with an initial velocity of 29.4 meters per second. And again, we have to label the directions as positive and negative. And so let's just draw out our situation here. We have a ball thrown upward at 29.4 meters per second initially. right? So it's being thrown upward. Here's the ball. But then we have gravity pulling down on it. Okay, and so gravity is going in which direction? Gravity is always pulling down in the opposite direction. And so because of that, we can label this as positive, the initial velocity, and gravity as negative. And because of that, let's put gravity as the acceleration, but negative. So negative 9.81 meters per second squared. That's really, really important. Okay, so it has an initial velocity of 29.4 meters per second. And then what's the final velocity? Well, 0 meters per second. And why is that? Why are we doing 0 meters per second for the final velocity? Well, remember that when a ball is thrown upward, we're looking at parabolic motion. And so if we have a graph like this, or parabolic motion, I'm just drawing this so that you can see it's really going up and down like this, but I'm drawing it like that so we can widen it and show it more clearly. When we have that parabolic motion, when it gets to the top here, this is going to be 0 meters per second. And why is that? Well, I'll show it to you right now.
So here I've brought you to a little video that, to be quite honest, makes me feel like I'm in the Big Bang Theory. This is 2025, but we're going back to a very old video. It doesn't matter though, the laws of physics still existed. And we can see this guy here. He's throwing the ball up first. And, well, as the ball's being thrown up with an initial velocity, which way is acceleration pointing, the vector for acceleration? Well, downwards, because acceleration is the gravity. And so gravity, when the ball is going up, is slowing the ball down. You can see as he throws the ball up, it starts fast and then it slows down as it reaches the peak of its parabola. It slows down because gravity is going in the opposite direction as the initial velocity. But then at the top, look at its speed. This is something that's hard for some people to understand. That at the top, the speed is 0 meters per second. Right there. And then the velocity changes direction as gravity pulls down in the same pulls down on the ball.
Okay, so now that we know just a little bit about why the final velocity is 0 meters per second, then we can plug that into our final velocity. So we have 0 meters per second, and then we're trying to find d. We're trying to find displacement, so find. And how do we know we're trying to find that? What is the maximum height reached by the ball? And then time, we don't know anything about time, unfortunately. And so which equation will we use? Well, we want to use an equation that has nothing, has no t, has no time. So let's go all the way back. Which one has no time? This one has time. We cannot use that. This one has time. We cannot use that. Great. This one. So let's use that one then. That one does not have time. So let's write down the equation. It is the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. Okay, but then what are we trying to solve for? Well, we're trying to solve for displacement. And how can we do that? Well, we can subtract the initial velocity squared on both sides, and that gets us final velocity squared minus initial velocity squared equals 2 times the acceleration times the displacement. And then we can divide by 2a on both sides, right, to get d. So then d equals final velocity squared minus the initial velocity squared divided by 2a. Amazing. So now let's plug in our values like we always do. I'll erase this over here so we have a little bit more room. Remember that we're calling up positive and down negative. So displacement equals, what's final velocity? Well, we have here that final velocity is 0 meters per second. And so it's 0 meters per second But that's all going to be squared because our equation says final velocity squared. Then that's minus 29.4 meters per second. That's all going to be squared because, again, that initial velocity in the equation is squared, and that is divided by 2a. Well, what's acceleration? Acceleration is 9.81 meters per second, right? Then times 2, because it's 2a, is 19.62 meters per second squared. Now, what I want you to do right now is I want you to pause the video and tell me what is wrong with my math so far. Did I forget a variable? Did I forget making something negative or positive? Did I forget maybe a unit? What did I forget so far in my math? I'll give you a second to pause the video. I'll show you everything on my screen. Just for this part over here, did I get something wrong? Or maybe I'm all correct. Okay, so hopefully you noticed that we needed to make that 19.62 meters per second squared negative like we talked about before. Super important. I want to make that crystal clear. And why is that? Well, it's because we're calling positive upwards and negative, then we need to call downwards. And so since gravity is always pulling downwards, we're going to call that 2a negative. Right. So now, let's keep solving. Displacement equals, well, we need to bring this exponent not just into the zero. This is something a lot of people get wrong, and I understand. Not just the zero, but also into the units, so the meters and the seconds. And so that would be 0 meters squared per second squared minus, well, what's 29.4 squared? 29.4 squared, that is 864.36. And then the units, remember the square goes in seconds, the meters, and the number. And so that would be meters squared per second squared. Remember that is over 19.62 meters per second squared. So now let's just simplify, combine. Let's simplify this numerator here. Put 0 minus 864, that would just be negative 864. And so this becomes negative 864 meters squared per second squared. Okay, great. And so now we just have the very simple part, okay? We've gotten to the easy work. Oh, and I almost forgot again to write this sign. See? I just want to make you remember, you have to write that sign. You have to call the upwards direction positive and the negative direction downwards. Okay, and so what is 864.36 divided by 19.62? That is 44.1. So that means our answer is 44.1. But wait, the units, what is meters per second, meters squared per second squared over meters per second squared? Well, that becomes meters. And that makes sense because we're trying to find displacement, which is in meters. Right, so our answer is 44.1 meters. And then what is the velocity of the maximum height? Well, we just discussed this with my video where we showed me throwing something and then it comes down, and we saw the maximum height, it was 0 meters per second. It was at rest. And so you can put 0 meters per second. Amazing. So we just have a few more questions left, so stick with me. Okay, so let's move on to question number 7. So I think that for question number 7 here, a rock is dropped from a bridge. What happens to the magnitude of the acceleration and the speed of the rock as it falls? We could just explain it and discuss it, but I think it would be much better if we go to a little simulator and we talk about what's actually happening while we test the situation, the scenario using the simulator. So let's go do that.
So here we are back in our simulator, and what I want you to do is I want you to imagine that this soccer ball is a rock. And so try to use your imagination. Imagine the soccer ball is a rock, and let's see Well, first guess what happens to the acceleration, which you can see right here, of the object as it falls. Well, remember, it doesn't matter how fast the ball is moving, neglecting air resistance, the gravity, acceleration due to gravity, will always be on Earth 9.81 meters per second squared. And so if we play the simulation, you will see that as the ball falls, the gravity stays at 9.81 meters per second squared. It doesn't matter how far or how fast it's moving. But what does a 9.81 meters per second squared acceleration mean? Well, we are also asked to find, well, how is the velocity going to change as it falls? And what does acceleration mean? Acceleration is the change of velocity. Acceleration means by how many meters per second is this object going to increase by every second. And so that means the velocity will increase by how many meters per second every second? 9.81 meters per second every second. And so if we look at 1 second, it will be 9.81 meters per second, and then it will keep accelerating. So the velocity is increasing. But what if there's air resistance? Then what will happen? Well, in our simulator here, we can choose large air resistance. Remember that it will keep accelerating until it reaches its terminal velocity, when the vector of air resistance, the force due to air resistance, equals the force due to gravity. So let's see what happens to the object now that there's air resistance. Now that there's air resistance, it accelerates at the start, but at some point, see, accelerating, but then the acceleration vector decreases because of air resistance, and then there's no more acceleration. It hits a constant terminal velocity of 4.9, in this case, meters per second. So, remember that the rock has, it's almost negligible, the terminal velocity, at low speeds because of its high mass in relation to its small surface area.
So I love that problem. It helps us understand so many things about air resistance, about how things fall differently inside a vacuum and without a vacuum, like we talked about before. It just covers a lot. So let's just continue now and move on to question number 8, where we're just doing a very simple problem like we've done in the past. Okay, just 2 more. You got it. So we have initial velocity, final velocity, displacement, acceleration, and time. So let's read the problem. A ball is thrown vertically upward with an initial speed of 26.3 meters per second. After being moving upwards, or after having been moving upwards for 1.8 seconds, what is the ball's speed? Well, let's label the initial velocity. The initial velocity is 26.3 meters per second. And remember, we're going to label if it's positive or negative. I'm going to say it's positive because we're talking about the first motion is upwards. And so I like to call the first motion positive just to make it a little bit simpler. And so initial speed of 26.3 meters per second. So 26.3 meters per second, simple. Okay, and then what's the final velocity? Well, after something, what is the ball's speed? So after is a great indicator of final velocity, right? So that means the final velocity is what we're trying to find. Fine, question mark, whatever you wish. And then for displacement, are we given anything about displacement? Nope. This is great because then we can use our favorite equation, at least in my opinion, the first equation, because it's the most simple. It's just final velocity equals initial velocity plus acceleration times time. And let's just, before we get too excited, let's just finish the data table. The data table, negative 9.81 meters per second squared. And why negative 9.81 meters per second? Well, because we called positive the initial upward velocity positive upwards. And so now, since it's in the opposite direction, we're calling it negative. Remember that with velocity or acceleration, negative or positive just means direction, kinematics. So time after 1.8 seconds. So we can label that as g for what we're given. Yeah, for our equation, we don't know anything about displacement, and which equation does not have displacement? Oops, sorry, too far. This is displacement. We will not use it. This is displacement. We will not use it. And so we'll use this one. Final velocity equals the initial velocity plus acceleration times time. So final velocity equals the initial velocity plus acceleration times time. And then for A, let's plug in our values. Final velocity equals, what's the initial velocity? 26.3 meters per second plus acceleration times time. Acceleration is negative 9.81 meters per second squared. And that is times, what's the time? Time is 1.8 seconds. Okay, let's do each side. So, final velocity equals 26.3 meters per second, nothing else on that side. So we just do 26.3 meters per second, easy enough, plus, well, what's negative 9.81 times 1.8? Let's do that on our calculator. 1.8 times 9.81 equals 17.658. But remember, this is negative because we're multiplying negative 9.81 meters per second squared times 1.8 seconds. And so this will be negative 17.658. I will just round to the nearest 100th and say 17.66. And then what are the units? Well, meters per second squared times seconds, meters per second squared times seconds. This here cancels out with this, and that gives us meters per second. Great. And then this plus minus here, plus minus just means minus. And what is 26.3 minus 17.66? That is 8.64 meters per second. Amazing. And then again, this is final velocity, so it makes sense why we're getting meters per second, right? Just make sure to check in and be sure that you are getting the units that you would expect from what you're trying to find. Great, so let's move on to our final problem. A brick, starting from rest, falls freely for 3 seconds. How far will it fall? So we're also going to use the lab to figure this out at the end, but first we do have to do the math to figure it out. So let's draw our classic table. We've been using this whole video. Initial velocity, final velocity, displacement, acceleration, time. What's the initial velocity? Starting from rest, so 0 meters per second. It's like this is a routine now. Falls freely for 3 seconds, so 3 seconds. And then acceleration is 9.81 meters per second. And you might say squared, and you might be saying, well, why is Henry labeling acceleration downwards as 9.81 and not negative 9.81? Well, I'm doing that because there is no upwards velocity here, no upwards displacement here. Everything in this problem is going downwards. And so it's easier to just label everything as positive. So since it's going in one direction, I'll just label everything positive. So now displacement, what is that? We're trying to find that. And we don't know anything about final velocity at all. And which equation can we use? We want to use one that does not have final velocity. Which one does not have final velocity? That would be this one has final velocity. Nope. I know it's hard to see. This one has final velocity. Nope. So let's use equation 2. Displacement. So d equals vi t plus 1/2 a t squared. And just to make this a little bit easier for us, it's the last problem. We do not need to do VIT here. And why is that? Well, it's because the initial velocity is 0 meters per second. And so since it's being multiplied by time to get this whole thing here, that will end up being 0. So we can forget about that. that is a gift for us. You can just forget about it. So displacement equal, although it is good practice too, if you want to, if you do feel like doing that at this point, 1/2 times acceleration times time squared. So we have 1/2. What's acceleration? 9.81 meters per second squared. And then what's time? Time is 3 seconds. But then remember to square it. Okay, so with 3 seconds squared, remember this squared applies to the seconds and the 3. And so that becomes 9 because 3 squared is 9. 9 seconds squared. Okay, so let's multiply 1/2 by 9.81 times 9. That would be 44.2. So 44.2. But then what are the units? Like we do always. This 1/2 doesn't have a unit, so we don't have to worry about that. Then meters per second squared times second squared. Remember, final question, we can remember this. Cancel that out, and then we just get meters. So let's bring that over here, and we get 44.2 meters. And before we go, just in case you really want to see that that is the correct answer, that I'm not just doing some crazy math, stay around. We're just going to show you the lab, and then we'll be done.
Okay, so we're here back in your guys' favorite activity in the I Want to Study lab, where we can see how objects fall. So what we're trying to find out again is after 3 seconds in free fall, what will the displacement of an object be? Whether it's a brick, a soccer ball, you name it. Not including air resistance, neglecting air resistance. And so let's play the video, the simulation. And now let's look at 3 seconds. So this x-axis here is time. And so we have 1, 2, 3 seconds. And then we go down here, and you see at 3 seconds, we see 44. Down here, we see 44. It's hard to show you, but down here, you'll see it. I'll zoom in for you. It says 44 meters per second. Meters as a displacement. Is that what we got? Let's see. Yep, that is what we got. We got 44 meters. So that means our answer is correct in a real life scenario.
Thank you so much, everybody, for watching that video. We learned about air resistance, how to solve problems with kinematics, how things fall differently inside a vacuum and without being in a vacuum, terminal velocity. We learned so much, and I hope you come back for the next video. Thank you.